Honored to be here. Thank you very much. We are here to discuss today the security of one of the most important technology ecosystems in the world. 2 billion active Android devices and counting. I'm Karsten. Over here is Jakob. We're part of a hacking collective out of Berlin and Hong Kong, where we do security research and also help occasional companies to improve their security. We want to take you today on what was for us a 2-year journey into understanding Android security. We'll summarize the highlights in the next hour for you. Jakob and I will give you different perspectives on that same journey. I'll be focusing on the research part of that journey, where we try to answer the question, what patches are installed on Android phones? And Jakob will explain the engineering components of that same journey, how we managed to answer that question at fairly large scale, hundreds of patches, thousands of phones, right? Patching, I don't have to explain to anybody, is critical to uphold the security of any system. No system is free of programming bugs, and as these programming bugs are being discovered, patches fix the vulnerabilities. And we do patch regularly, pretty much all our IT environments, and in most IT environments, we have a fairly straightforward patch ecosystem. We have a vendor, say Windows, a Linux distribution, Apple, issuing patches, and then users installing those patches. Sounds pretty straightforward, but anybody from an enterprise environment, of course, knows what a huge headache patching can be, even in a simple ecosystem like that. Organizations spend a lot of time on monthly patches, or have even given up on monthly patches and only patch once every 3 months or per year, even in a simple patch ecosystem. Now look at Android, so much more complicated still. In Android, you don't have one vendor issuing patches and then all the users installing it, but rather you have Google maintaining the security of this ecosystem by creating patches, but then Google issuing those patches to the chipset vendors. Well, they make them publicly available, but the chipset vendors consume them. Qualcomm would be an example. Merge them into their own modified versions of Android, and then issue those modified versions to their customers, companies that build phones, like Samsung. And then Samsung, once again, would take the patch that they receive from Qualcomm and merge it into its modified version of Android. And not just once, they maintain hundreds, or in the case of Samsung, probably thousands of different Android builds in parallel for different versions of different phones. And then many of those need to be shown to mobile networks all over the world to get an approval that those patches can indeed be issued to the customers, right? So a long chain of companies is involved here. And the research question that we have is, how many mistakes are being made in this very complicated multi-step process? How many patches get forgotten, right? A question that hadn't previously been asked. Now, if you want to figure out how many patches are installed on a given phone, you would perhaps just think to look into the settings menu. It says patch level date, whatever it says for your phone. Now, that would be one way to answer which patches are installed, but we did learn from an example about 2 years ago, not unlike this one, that these patch claims can be unreliable. So here's an example from last year, a phone whose patch level date says September, but as these red boxes indicate, the patches from September are not installed, and neither the ones from August, July, going back many months. So here's a vendor that more or less arbitrarily set this patch date to whatever they thought looked good, without actually doing the work of installing the patches. So we need another way to verify whether patches are installed on Android phones. Now we could go the exploit route, knowing that a patch is needed to prevent a certain exploit. We can try the exploit, and if the exploit still works, the patch is missing. But exploits are not available for most Android vulnerabilities, and even if they are, they don't really work reliably, so you never know. Did it fail because the patch is installed? Did it fail because something else in the environment isn't right for this proof of concept exploit? So this will not give us a complete picture of Android patches. So we chose a third way, analyzing the software running on a phone or inside a firmware file to determine which patches are included on that phone or in that firmware file. And that's the journey we want to take you on today. Let me define this question a little bit more clearly, though. When we speak about Android patching, we possibly mean two different things. So primarily, there's Android, the operating system, well-maintained by Google, well-versioned. It's understood what's included, which patches should be included. That's the one side, and that's the more important side when it comes to patching, because the hacker from the outside will always first hit the Android system, before then later perhaps wanting to leverage some vulnerabilities in the Linux kernel. Let's not forget, in each Android phone, there's also a Linux kernel running, which is not maintained by Google. This is maintained by, of course, a much larger ecosystem of companies and individuals. And Linux is designed for all kinds of things and servers, maybe the occasional desktop. So many security patches for Linux don't necessarily apply to Android, right? Also, it's less important because, as I said, the attacker always first hits the Android layer and maybe only later wants to exploit further into Linux. So for the purpose of this discussion today, we're not going to look at the Linux side, but focus on Android, the Android patches, right? So yeah, that clearly defines now why we did this research and what the research question is. Which patches are installed on a given Android phone? And this question needs to be asked hundreds of times because for Android there's a bunch of different patches. So last year alone there were about 1,000 patches, security relevant patches for Android. Some of them are for the Linux kernel, so let's exclude those for the moment. Some of them are marked as low or medium severity, so we're not going to look at those. But even in the bucket of high and critical patches, just on the user land, there's about 300. So that's a good place to start our research, 300 patches. About 80% of them, you can download the source code, mostly from Google. And so you understand what is the patch, what changed in the source code. Another 20% roughly, they are proprietary code patches. So Qualcomm, for instance, would say, we patched something, but we're not going to tell you what it is. It's a little bit difficult for us to then measure whether the patch is installed. So for the moment, we're ignoring those. And we're also focusing on C and C++ code, just because we got to start somewhere. So we're losing a little bit of coverage over Java. But at the end of the day, we created heuristics for 164 patches issued last year. And each of those patches typically measured through different heuristics, so that if you have multiple tests for the same patch, and they all come back with the same result, we have a high confidence that this patch is actually present. So we have these hundreds of tests, and we'd like to run them, of course, well, if possible, all Android builds. How many Android builds are there? Apparently there are more than 60,000 different models, Android models, and each of them, well, not every one, but many receive regular security updates or functional updates. So there's hundreds of thousands of Android builds out there, right? So optimally, we would run this as a large-scale experiment. And we have, as far as possible, and looked at a bunch of different phones. Now, let me first give you some of the results of this analysis, and then later explain how we reached those results. Here are the patch results for 4 phones, and those cases are chosen to be kind of representative corner cases of the option space. So all other phones would fall somewhere in between those 4 examples. And on the x-axis, you see those 164 patches that we're testing for from 2017, plus some more from 2016. So let's start with the Google phone. It includes all patches from last year, no exceptions. And that's by definition, because this phone runs a very recent Android version, 8.1, and that by default includes all previous patches. Like in Windows, the service packs, they include all patches that were issued before the service pack. So if you move to a recent Android version, that means you don't have to worry about any patch issued before that version, right? So Google seems to put a little bit more effort into moving their phones to new versions. They have to, of course. Their phones are kind of a laboratory environment showing the rest of the ecosystem that is possible. But that means that they have to spend less time on patching the phones, right? Android on Samsung is maintained in a somewhat different way. Many Samsung phones have not upgraded to Android 8 yet. So, for instance, here's a Samsung J5 that has a lot of patches installed from 2017. In fact, as far as we can tell, all the patches up to November were individually installed on this device, with one exception. One patch from September is missing. And I don't know the backstory. Maybe it didn't apply that patch. Maybe Samsung modified that part of Android so much that now they have to reverse engineer how to apply the patch. For some reason, Samsung didn't apply this one patch. But they're honest about it. They say the patch level is August. So they say, we guarantee that the patch is until August installed. And because of this one missing patch in September, we're not increasing the patch level, right? But that very same company does not always make that choice consciously or subconsciously, I don't know. So a related phone, also 2016 phone from Samsung, also J series, runs on an even older Android vintage, Android 5. So Samsung has put years into maintaining patches on this phone rather than just moving it to a more recent Android version. But that's their choice. I'm not judging. But they are missing a bunch of patches. So this phone claims to be patched January 2018, which suggests that all patches from last year would be included. But they're not. There's 12 high-end critical patches, as far as we can measure, missing from this phone. Right? And that is the Android patch gap. And the Android patch gap is even larger for some other phones. As an extreme example, look at this phone. The dark green patches, they're not necessary for this phone, and all the red ones, they're missed. So this phone claims to have been patched in September, but really hardly anything was installed in terms of patches for an entire year, right? So this is a case of a vendor that I think just arbitrarily set this date to whatever they thought their customers expected. You remember how we, as a community, we pressured Android vendors into saying, yes, you'll get monthly patches. Well, they give you monthly patches. They change the version string every month. Right? So this is from a manufacturer called Vico. Let's remember that name. They'll come back a little bit later in this presentation once again. So these are the results, but let's now dive into how we got these results. How do we do Android patch analysis? I'll only explain this on kind of a simplistic level, and then Jakob will dive into all the juicy details. So simply speaking, what we do is we take the different Android source codes, right, from Google, from Qualcomm, whoever. We take them without the patch, and then we apply the patch. So we have these two sets of source codes, and we compile these two sets of source codes a bunch of times with different compilers, with different compiler options. So we have these two collections of binaries, one without the patch, one with the patch installed. And then from all these binaries, we strip out the function that we're interested in, the function that was affected by the patch. And then we go one step further, we look at the function, we remove values that have arbitrarily changed with each compilation. For instance, destination addresses in a call. Right? We strip out those values, just overwrite them with zeros. So we have those two sets of binaries or functions now with those values zeroed out. We can call them signatures. Right? So that's a preparation step, creating these two sets of thousands of signatures. And then when we actually want to test one phone or one firmware, we take the binary that's inside that firmware. And again, we take the function, we strip out those volatile values, and we just compare it to our collection. And either it matches one of our samples that has the patch installed, or it matches an example that doesn't have the patch installed. Right? So just kind of by brute force, we find an exact match of that function, and we know whether or not the patch applies. Right? So In theory, that sounds pretty simple, but when applying this to hundreds of patches and thousands of phones, of course, things get a little bit more complicated. And Jakob will walk you through those engineering questions. Personally, I thought some of these engineering solutions that we found were among the most interesting part of this research. And I think they would also apply to a bunch of other problems that you may have in terms of software scale, but judge for yourself.
So before I go into the details of doing the patch analysis, I will quickly summarize the process from source code in the source code tree to the binary file we find on the device. So the first step is compiling it. So the compiler reads in the source code, pre-processes it, takes all the included files, which may be somewhere completely different in our source code tree, replaces the preprocessor variables, and then compiles it to binary code in the object file. But in the binary code, we do not yet have the destination address for some call instructions like here. And then the linker takes a number of these object files from different source code files and combines everything together into one single executable file or a shared object file. And the linker fills in the missing parts, for example, the destination address here. So let's take a quick look at one of these object files. We have a disassembly listing here of one typical function from an Android system. And here we see a call instruction, and here we see the relocation entry. So this tells the linker that in this instruction, the last 26 bits needs to be replaced with the destination address. And so we can record that at this position in our function, we have this type of relocation entry, and these bits needs to be stripped out. And then we also have to store the length of our function and the remaining source code after stripping out the bits changed by the linker, and we can hash the remaining source code and then later on compare this hash with the code from our device. So things look pretty simple in theory, but in practice it gets a little bit more complicated. We have to deal with a large amount of source code, and we have to deal with many different compiler versions and also compiler options like CPU type or optimization level. And last but not least, we will have to find the code in our device. So let's see how the Android source code is organized. If you want to download an Android source code tree, you will have to use the repo utility. Repo is basically a repository of repositories. So we have a master repository, which contains only one manifest file, one XML file, listing all the Git repositories needed for this Android build, and the exact revision in this Git repository. And we have about 500 repositories in total, and if you download everything, you will end up having about 50 gigabytes of source code for one source code tree. But for our analysis, we need many different Android versions, many different source code trees. So as a user, you may know that your phone is running Android 7.1.2, but even within this version, there are many different revisions with a different set of patches applied. And so we end up with a couple of hundred different Android versions alone from Google. And additionally to that, we also have some device-specific source code trees. So for example, Qualcomm releases many different Android versions for different chipsets and different Android versions and patch levels and so on. So in total, we have currently about 1,100 different source code trees. And if we need 50 gigabytes for each of them, we will end up with about 55 terabytes of storage and also lots of CPU time and network bandwidth to check out everything. So we should rather find a better way to deal with that amount of source code. But if we take a look at a couple of these different Android source code trees, we will find out that they all reference the same individual Git repositories, but different revisions within these Git repositories. But many of you are probably using Git, and you may remember that when you clone a Git repository, you are actually downloading the full version history. So you are actually downloading all revisions from this Git repository. So we only have to download each Git repository one single time. But in order to compile the source code, we still need to have access to a full Android source code tree. And so we decided to implement our own file system. This file system is implemented in user space based on Fuse. And our Fuse file system will read in the manifest file and then check out the files from the individual Git repository metadata on demand only. So only when we try to read the file, it will actually be extracted from our Git repositories. And this reduces the storage requirement by more than 99% and also saves us lots of CPU time and network bandwidth.
Yeah, I thought this was one of these engineering solutions that would probably apply to a lot of other problems as well. Whenever you have very redundant data, for instance, from a bunch of different gets stored in one file system, storing it in a file system that is aware of that redundancy and helps you remove it can save you a lot of time, storage, and bandwidth, not just around Android patch level analysis.
So now that we are able to handle all this data, all the different Android source code trees, we can actually try to compile it. We don't want to compile everything in our Android systems because this would take a couple of hours for each source code tree. So we just run the build system in dry run mode and record the comments which it would use to compile everything. So we then take these comments, but only for the source code files we are interested in. And when we compile it with a couple of different compilers, with more than 50 different compiler versions, and for each of these compilers, we have different optimization levels and CPU types. So we have a couple of thousand different variants to compile it with, but we will have to see how many of these are actually required. So for that, we have a collection of firmware image files on a server, and we can quickly find out which of these compiler variants are actually required to create the signatures which match on our collection of firmware images. And as it turned out, only 74 different compiler variants are actually required from a couple of thousands we have tried.
Yeah, and note that this slide, of course, includes the most successful compiler ever used, right? This compiler is used for the firmware of more than 1 billion devices easily, and it's a pre-release version, right? How successful for pre-release. So up to this point, I guess we now understand how we can compute these two sets of binary signatures, right? The ones without the patch, the other one with the patch, running 1,200 different source code trees through 74 different compiler versions. And so, Jakob, what are we going to do with this collection now?
So once we have our collection of signatures, we can actually verify the patch level of our device. And in many cases, it is relatively simple because the file we are testing has a symbol table, and the function we are looking for is actually in the symbol table. So we know where the code is. We can extract the code from the binary file on the device and see if one of our signature matches. But in other cases, things are a little bit more complicated. So in some cases, we don't have a symbol table, or we do have a symbol table, but the function we are interested in is not in the symbol table. So we have to find our function in the whole binary. And this is a computationally hard problem. We can't really compare each signature at each position in the file, so we have to find a better way. And fortunately, a similar problem has already been solved in a completely different context for file synchronization by the rsync utility. And they have implemented a rolling checksum algorithm, so you can easily slide a checksum window over a binary file and calculate the next checksum with very little effort. But unfortunately, we can't directly use this algorithm because it will only find exact matches. But as we have seen before, there are some volatile data within our functions which we can't compare because it changes on every device. And also the rolling checksum algorithm is only efficient if we have one window size or maybe a very small number of window sizes. And so for the first problem, we just take a look at the instruction opcodes and we guess whether it could be a relocation entry based on the instruction opcode. So in that case, we see a call instruction, so we guess this is probably a relocation entry and we zero out the arguments. And then we are not using one checksum window for each window size for each signature. Instead, we are using window sizes of a power of 2 only, and we are using 2 overlapping windows. One at the start of our function here, and one window at the end of our function here. And if both window matches, and only if both window matches with the right distance, we have an actual match, and then we can actually use the saved relocation entries from our signature and confirm that the match is correct. There may be some false positives when guessing the relocation entries, so we have to do this confirmation step.
Yeah, this is probably my favorite kind of engineering hack that we came up with. because it solves a pretty generic problem. Usually when you do any kind of signature matching, the number of matches that you need to check for scales with the number of signature sizes, right? If you want to match small and medium and large things, you have to run everything 3 times, and it scales in the number of signature lengths that you have. Now with this solution, it doesn't scale in the number of sizes anymore. Instead, you only check 2 times your original number of matches to gain any number of signature lengths, right? So you gain an entire degree of freedom in signature matching by doubling your initial effort, right? I think this was pretty neat, and you should try it if you do signature matching.
So now that we have solved our engineering challenges, we can put everything together. So we take our Android source code trees and then generate a build log, compile the files we are interested in with many different compiler versions and compiler options, and generate signatures based on that. And then we can find our code in the binary we are testing and find out whether the signature matches or not. And if we have a signature match, we can look up whether the source code used for generating the signature is patched or not. And if it is patched, we know that our device is patched as well, and vice versa.
Yeah. All right. So that was the engineering journey to now be able to apply these signature matches across a large number of different patches on devices, and to do that at scale. That means, for instance, for us to run it on the device itself. Right? That was one of the optimization criteria that we had. And we did that for thousands of devices to reach these insights. Different vendors have different quality levels when it comes to patch completeness. Some vendors are very close to installing all patches. Of course, Google is the reference here because they need to show to everybody else in the ecosystem that it's possible to install these patches. So they are the most complete usually. But then even Samsung improved dramatically over the last year. So where we showed one example on an earlier slide was 12 patches missing. That is rare for Samsung in recent months. We're only looking at data since October here. And even our friend Vico made it into this top list. So remember the company that didn't patch at all and kind of arbitrarily set this patch date. They have come around and in recent versions do patch a lot more. They're following a little bit the Google lead in just moving to newer Android versions more quickly, so you don't have to patch so much, kind of the whole service pack idea. And I think that's a good idea. I think everybody needs to install new Android versions a lot faster because it gives you, on top of all the security patches, new security functionality usually, better randomization, those kinds of things, right? But yeah, some other vendors on the other end of the scale that do like quite a number of patches on average, and for certain devices, dozens of them, right? However, not every missing patch is due to the vendor forgetting to do something. Often those problems start earlier in the patching chain at the chipset vendor, right? You can see one chipset vendor here that's used in more economic devices. And it would appear that chipset vendor already forgets to include some patches when issuing the source code to the phone vendors. And then most of their customers would miss those patches. I don't think that explains the gap between MediaTek and its competitors completely. I think this is the compound of 2 factors. One is that MediaTek may forget some patches, but the other compounding factor is that if you're already making economic choices when it comes to chipset selection, if you're already going for a cheap option there, you may also make economic choices when it comes to maintenance of those phones. So you may not put in quite as much effort as for your top of the line phones, right? So important to say that, of course, not every missing patch is automatically an open vulnerability, right? But still, we find a bunch of missing patches. What can we do with them now? Can we use them to hack a bunch of different Android phones, as the previous slide would suggest? And intuitively, coming from more like a PC Windows background, we would think, yes, of course, there are patches missing for CVEs with CVSS scores of 9 and higher. In the CVE, it says code execution risk, right? You'd think that if a patch like that is missing, then there's an immediate exploit risk. But we're not dealing with Windows here, right? We are dealing with a different kind of operating system, one that was built with more security technology built in from the first place. And not just Android, all of these mobile operating systems. They include things like sandboxing, right? So this already builds an additional security barrier, but also includes things like randomization, memory layout randomization, not just for system and kernel, but more and more mandatory for every single application running in this operating system. So where do we fall in this trade-off? Is it easy to exploit it now, or is it still hard because it's a mobile operating system? Well, if we look at the criminal ecosystem for their answer to this question, by and large, criminals say, we're not going to exploit Android because we don't have to. If we want to steal the data of an Android user or take over the phone, not necessarily a user, but a large number of users, will suggest that they should install some malicious application. And enough users will do that, so I don't have to do any hacking. Right? A lot of mobile phone infections in Android, in fact, the vast majority of them come from downloads that the user initiated, installations that the user wanted, usually under pretense, right? The user doesn't say, please hack me, right? Rather, they would say, I want to install this pirated version of the software, for instance. And of course, Google is going through great lengths in securing the Google Play Store. There's still malware flowing through the Play Store, but it's becoming less and less. But that only covers some part of the ecosystem. China, for instance, obviously a huge Android market, only 4% of the users in China use Google Play at all. So 96% of users in China will not benefit from anything that Google does through Google Play. So this will continue to be a problem. Now, the little bit of hacking that we do see that criminals do is then the second step in hacking. Somebody installs an app on their phone from some pirated version, for instance, and then this app will either ask for permissions or it will hack into the phone, use what we will call routing techniques to gain additional privileges. But even here, it's often easier to just ask the user for permissions. For instance, the device administrator permission is a very powerful one and basically prevents the virus from being uninstalled, right? Once you grant device administrator to a virus, basically you can't remove it from your phone anymore, right? So the hacking that we would imagine happening around Android is not publicized. There's no public information on any Android hacking happening, let's say, over the last 12 months. But of course, it still happens in corners of the ecosystem, state-sponsored, otherwise very determined and persistent attackers. And those would oftentimes use 0 days. But nobody can hack Android just based on one bug. So let's zoom into that corner of the ecosystem. And even if it doesn't happen right now, as a researcher, I'm interested in the question, can it happen? Can somebody remotely hack my Android phone without me installing a malicious application? Right? So let's first look at which of those missing patches that we find we can use in exploitation, because it's important to state that not every missing patch is an open vulnerability. And we know that from all other operating systems also. It's just important to summarize it once again here. A patch missing could be explained by the phone vendor saying we found an alternative way to fix the same vulnerability. We have seen rare cases of that happening, where apparently the Google supplied patch didn't work so well in that modified version of Android that a vendor uses, so the vendor just created a different patch. So then our analysis would correctly state the Google issued patch is missing, but that would not mean that the vulnerability is open, right? So these gaps do exist. And then on top of that, of course, some patches rely on certain configuration settings. Remember the vulnerability that led to WannaCry? You could defeat that by just switching off a certain version of SMB, right? So you didn't have to install the patch. There were other configuration settings you could do to prevent that exploitation. And the same is true, of course, for many exploits, that they rely on some environment variables. And then finally, some bugs get submitted that just can't be exploited, right? Relatively little research goes into actual exploitation relative to finding the bugs that could be exploited. So there's always a little bit of a gap there. And then finally, our analysis could be wrong, right? And it has been in a few cases. It's becoming better and better over time. But of course, we could be saying a patch is missing where in fact, the manufacturer just changed Android in such a way that lets us to believe it's missing where really it isn't. But yeah, so that would mean that if there's only, let's say, one patch missing on the phone or two, maybe those aren't actually leading to any open vulnerabilities. But some of these phones we look at, they miss a whole bunch more. And so chances still are there are some open vulnerabilities on the phone. And what can we now do with those open vulnerabilities? Well, according to the textbook, you would need 4 vulnerabilities to hack into an Android phone. Now, there's alternative paths, but this is kind of the standard path for vulnerability, for full exploit. First, you need to peek into the memory of an application. That's because each application is launched at a kind of random position every time you start it, address randomization, and you need to know where your application is running right now to exploit it, right? So that's the first one, and that already requires a bug, so a missing patch. That's number one. Second, you then need to inject executable code into that application or play around with jumping to code that already exists there. So you need to inject something. You need to corrupt the memory. That requires a pretty good a bug or a second missing patch. And after those 2 bugs, you're in the application context. So let's say this is a messaging application. So now you can read the messages, but you can't hack the phone yet. Right? You want to breach out of that messaging application and take control of the whole phone. And that means you have to go through this whole process yet one more time, again 2 bugs, an information leak and a memory corruption to breach into either a system context or into the Linux kernel directly. 4 bugs necessary to exploit Android, right? According to the textbook. Mileage may differ. And if you do look at successful exploitation, now not the criminal part of the ecosystem, as I said, we have very little information on how that works, but published research results, we do find that by and large, this 4-bug rule holds. Let's start with stage fright, of course, the most famous Android bug. It never worked. Stage fright is one of 4 bugs in a chain, and nobody ever put it together in a chain of 4 to exploit an Android phone. In fact, even the very first step in the chain didn't work. The peeking into memory, deriving the memory location, to my knowledge, nobody has shown to combine an information leakage bug with stage fright yet. So stage fright is an example of a bug that if it is the only bug on your phone, chances are you don't have to worry about it, right? It needs to be combined with other bugs. Now, the second one, that's probably the most interesting case, because this is the one example of a bug that we could find that actually does check all 4 boxes. It's confusingly named similar to the stage fright. The technique is called return to lib stage fright. It is a single bug that is just so versatile that it's both information leakage and memory corruption, both in the user context and in the system context. So that was the one time in recent history that we saw a single bug taking a hacker all the way from outside the phone all the way to a system context, right? That was patched pretty quickly and consistently on a lot of phones, but it's important to remember that a bug like that has existed so that no vendor can get away by saying, oh, we can forget a few patches, no single patch matters, right? This one would have mattered a great deal. But all the other published research results, they build exploit chains where more than one exploit is necessary to breach these different security layers. As you see here, these chains unfolding. Right? We did include some more explanation of these chains in the slide. I'm not going to go through detail. I'm just showing this to you. So when you download the slides later, you can look into this deeper. And do let us know if you know of other exploit chains. We're really curious to see kind of the structure of exploitation and to see whether, for instance, this return to lib stage fright is very efficient one exploit bug, if there's more cases like that, or whether that was a total anomaly and fluke and we shouldn't expect anything like that again, right? That's an open research question for us. Another way in which we want to engage you is to give you the opportunity to measure the patch levels on your own phones. After all the engineering that Jakob and the team did, now there's this large analysis runs inside an app on an Android phone. And in fact, we took an app that we had already released a couple of years ago, Snoop Snitch, whose main goal previously was to find IMSI catches and other types of mobile abuse. And we extended this app to also now measure Android patch level. So that's freely available on Google Play, and it's also open source. Probably the latest version isn't published as source code as of today, but that's going to come in the next couple of days when we had a chance to clean it up. And we hope that you and many others can use this to either gain confidence into the patch levels of your phone or to spot gaps and help us publicize and get those closed. Right. So that was a 2-year journey for us, both a research and an engineering journey. What did we learn? So personally, I don't think I changed my views on Android very much through this research journey. I still believe similar things than I believed, let's say, a year ago, but I believe them for different reasons now. A year ago, I thought we had finally convinced the Android vendors to do monthly patches. I saw those patch dates increasing every month, and I was happy that unless somebody's dealing in 0 days, probably I was safe. Now, I learned that that's not the case through this research, and that, in fact, some vendors have pretty significant gaps in their patches, and that will only improve over time. But I realized also that missing patches are not as significant on Android as they are on Windows. A single critical patch is rarely enough to exploit an Android device. And that, again, gave me more confidence, not so much in the vendors who are forgetting the patches, but more in the ecosystem as a whole. So right now, I think it's fair to say that this is a better protected system than a lot of Windows environments. And assuming that the same data lives on your Windows computer, in your corporate environment, and on your Android phone, chances are it's easier to hack it on the Windows computer. But of course, again, your mileage may differ. It is also fair to say, though, that the hacking incentives around Android are only going to go up. Android is such a popular, successful technology, and with success comes responsibility. Responsibility for the data of an increasing number of people who rely on Android as their only computation platform, who don't have the same data stored on some corporate Windows computer also, who really have to trust Android and Android only to keep them secure. And I think that part of the population and ultimately, many people, including us, relies on the vendors maintaining their ecosystems to higher quality standards that our research has shown some of them to do. Right? So I hope that this journey continues involving a lot of you, and continues involving a lot of vendors, and based on a more open dialogue, based on actual facts, not random strings set in some firmware, so that we can then close these patch gaps and live up to the responsibility that Android should have, given that 2 billion devices are currently using it. Well, with that, thank you very much, and thanks for coming onto the journey today. So while we are handing over the microphones to the first questions, let me just thank my team in Berlin for just extraordinary work here. I'm always impressed working with those geniuses, and this research wouldn't have been possible without him. So thanks for everybody on this slide. And while we're at it, if you find a project like this intriguing, the research and the engineering component, we're always looking for more talent. So if you're interested in doing projects like this in Berlin or Hong Kong, come speak to us later. Thanks. And now over to your questions.
Okay. Hi, thank you for the talk. Did you try the BlackBerry devices?
Did we try what?
The BlackBerry devices.
Did we try BlackBerry devices? We have. Now let's go back to this slide with the overview. BlackBerry is not included on this list because we had too few samples. We have too few samples from two types of vendors. Either vendors who have not patched anything since October, they can't be in our data set because we only measure patch levels October or later, but BlackBerry is not that part. It's just not so widely used that we would have many samples, but you can change that, and many of you already have. Perhaps some of you saw the Wired article yesterday that also mentions our app. That already drove a lot of downloads and tests, so we have a more complete test set now, and BlackBerry will definitely appear on the next list, and we'll maintain and keep updating this list on our website as rlabs.de, right?
Okay.
Yeah.
Thanks.
Other questions?
What are you planning to release some parts of your research, like which vendor, like either the source code for what you did, or like the results, or something like that, or?
Yeah, well, obviously we're doing research so others learn from it, right? So we're releasing as much as we can. The application, the Android application, that's open source, so you can do whatever you want with that. We also released the actual measurements behind this table to each of the vendors affected so that they know what their individual gaps are. And we started some really good dialogues with them around how those gaps came about. They also helped us understand that in a few cases we measured wrong, right? It's a super good dialogue. While this dialogue is happening and while we're learning from each other so much, I don't think I'd want to make the raw data public because it's only going to trip off the wrong people into exploiting, adding some of those to their own exploit chains, right? So I want to give the vendors some time to respond to this because they didn't have very much responsible disclosure time at all. They only saw this data about a week ago. Yeah, but at the end, I mean, we are working for the community, right? I mean, this data is for you and we'll share it as much as we can. There was one question over there.
I just installed your app, and when I started it up, it asked for super user permissions, and I wondered why it was doing that.
Yeah, you're one of our few users then who has a rooted phone. So, of course, most phones are not rooted anymore, and we wouldn't advise it, right? Because we have seen a bunch of malware actually looking for root permissions, and if it's there, even better, let's just exploit that. But if you do have a rooted phone, then this app does a lot more than just patch level analysis. You can see here in the pictures that you can measure the encryption properties of your network, and you will be alerted when you're latched onto an IMSI catcher, like a fake base station. But in order to get kind of the raw network measurements, to find those IMSI catchers, we need root permissions. We need to read from a file that's not usually readable, right? Okay. Yeah, so sorry for conflating different things. If you came to this app with a rooted phone and only wanted to do the patch level analysis, then I guess you got more than you asked for. Right? Other questions? Well, we're obviously around for the rest of the day, so come speak to us if you're too shy to ask your questions now. And yeah, thanks again.